entire, they have to replace the sink or the entire countertop, and which is thousands of dollars. So this particle-filled composite, it has ATH, aluminum trihydrate, which is like a ceramic particle in the middle. These are the filler particles. And the matrix is polymer, PMMA. And then they use a binding agent between the filler and the matrix. The filler itself is polycrystal. It has many crystals in it. So if you look at it under the microscope, it looks like this. So this is one filler particle, what they call ATH, alumina trihydrate, hydrate, this piece. And they are about 35 micron in size, but it has many crystals. Like, for example, this is one crystal, this is another crystal, another crystal, another crystal. And this is inside the polymer matrix. Now, so to be able to improve the lifetime, I mean, they don't mind if it cracks, but it should crack after 10 years, after the warranty expires. What company, when they give you 10-year warranty, they want the system to fail 10 years and 1 day. But they don't want. So they said they cannot, they gave us parameters that we can change and parameters we cannot change. Like we cannot change the polymer, the matrix, PMMA, and then we cannot change the filler, the ATH, but however, we could change the binding agent between the polymer and the filler particles. So we made 3 different composites. One is, we'll call it A. We use a bonding promoting additive. So the bond between the matrix and the filler is very strong. And the matrix is 52%, particles are 48%. So we kept the filler volume fraction same and particle size is same. The second composite, we didn't use any additive to promote cohesion between the filler and the matrix. And then composite C, we used the debonding agent that promoting essentially debonding. Essentially, the fillers are inside the matrix, but there is no bond between them. So you cannot transfer the strain from ceramic, very, very strong, has a much higher elastic modulus. So there is a coefficient of mismatch between these 2 materials. The ATH particle coefficient of thermal expansion is 14.7 to the -6. The polymer coefficient of expansion is 88. So more than 5 times bigger. So when you dump hot water into the sink, they expand at different levels. And then the Young's modulus also, okay, somebody sent something in the chat. Okay. I'm sorry, the Young's modulus for the particles, it is like ceramic type of a material, alumina. It is essentially ceramic. 70 gigapascal elastic modulus. So it's very, very high. If you think about steel has 200 gigapascal, the elastic modulus is 1/3 of the steel. But however, for the polymer, the elastic modulus is only 3.5 gigapascal. So it is very, very weak. So that means any load is carried by the particles. And the Poisson's ratio for particle is 0.24 and Poisson's ratio for polymer is 0.31. So you could consider those are not same, but close. Not the difference is not like Young's modulus. Now, here is a picture that we take stress fringes. One is at 90 degrees Celsius, and then one is at 22 degrees Celsius when we applied loading in the system. Now, 90 degrees Celsius polymer is near glass transition temperature. It doesn't carry much. The elastic modulus of the polymer is near 0. Okay, my computer is not going to the next page. I don't know why. Can you hear me?
Yes,
Yes,
we
sir.
Yes.
You can hear me. Okay, I don't know why my computer doesn't go to the next page. I'm gonna get out of this and get back again. I don't know what happened. Escape doesn't work. Let's try to Control Alt Delete. Okay. Okay, I was able to go to the next page. So we are going to study the influence of interfacial strength because the reason in composite you have two materials, you want to use strength or advantage of each component in the composite. But for these two components here, the matrix and the polymer, to be able to talk to each other, transfer strain from one part to other, there has to be interfacial strength. And then temperatures, of course, is very important. And then we looked under uniaxial, tensile, fatigue, and thermal cycling. Now, for composites, most important thing is the mode of failure. The question is, how do they fail? Okay, so of course we are taking one particle here, this 35 micron piece. Now, one way it can break, what we call the particle can break, but matrix is still intact, or the matrix can break and then take apart the particle. So this is called particle breaks first, filler particle, and here matrix breaks. Or another possibility of failure is debonding of the particle from the matrix. So these are three different failure modes. Now, when we test these composite A, B, C under uniaxial strain at room temperature, so again, composite A, we have a cohesion promoting agent between the matrix and the filler. So that means that the bond between the filler and the matrix is very strong. We are using something like a glue to improve the adhesion between the matrix and the filler. It gives us the highest ultimate stress, almost 50 megapascal, but however, it is very, very brittle because the fillers are ceramic, and ceramic is a very brittle material. It governs the stress-strain response of the material. Now, and then composite B, we don't use the adhesion promoting special glue between the filler and matrix, but there is still cohesion between the matrix and a matrix and the filler. The ultimate stress goes to 40 megapascal, but it is still fails almost at the same strain level. It is very brittle material, so it's still filler particles are carrying the load. However, if we use a debonding agent, so the matrix is unable to transfer the strain to the particles. So essentially, we are getting response of a polymer with no particle, almost no particles, because this is composite C. In composite C, we said we are using a debonding agent. So we are making sure that the particles do not bond to the matrix. So as a result, there is no interfacial strength. And polymer is, of course, a very ductile material. However, the ultimate strength went down significantly, but the ductility increased by orders of magnitude. Now, and then we run fatigue test, tension compression fatigue test in these samples. Again, we have A, B, C samples. And then we run them at different temperatures. At room temperature, when the strain amplitude, this amplitude is 0.6%, it fails in 104 cycles. And then we test composite C at room temperature. Remember, composite C, there's a debonding agent between the filler and the matrix. So fillers are just floating inside the matrix. So you are getting pretty much in the tension zone, you get the response of the polymer, right? But however, when you go into compression now, in compression, you don't need a bonding agent between the filler and the matrix because you're pushing against the filler particles, and then you have much stronger elastic modulus because this curve is stress versus strain. And if you remember, slope of the stress strain curve, we define it as elastic modulus. So that's why you get a different elastic modulus in tension versus in compression. Even though the particles are not connected to the matrix, but when you go into the compression zone, it doesn't matter. The matrix is pushing against the particles, and particles are very strong, ceramic. As a result, you have, again, a different response in the compression zone than tension zone. In the tension zone, pretty much you have a polymer. And then in the material, you can measure damage by different metrics, right? In the measurements, you can measure the elastic modulus degradation, you can measure the plastic strain range, load drop, the maximum stress it can take in each cycle continuously goes down. Like, if I go back again, the That this is the stress level in the first cycle, and then continuously it goes down. So this decrease is called load drop. And then hysteresis energy, that energy also goes down in every cycle. The area inside this curve is called the hysteresis energy, and that area goes down in every cycle. So now we have to model this composite, of course. So the interfacial properties between the matrix and particle and is very important. That has to be accounted for. The CT mismatch between the matrix and particle is important. And there has to be degradation, damage, that the stiffness of the matrix is degrading at the interface, at the polymer level, and in the filler. And of course, in unified mechanics theory, the damage evolution takes place according to second law of thermodynamics. So, how do we model a composite material? Now, if I look at this material under a microscope, this is what I see. So these scruffy pieces are the particles, and this smooth surface is the matrix. So if you break it in two, okay, this is what you see. Now, how do we model this? Now, of course, in engineering, we make assumptions. We cannot model exactly. We don't have the computational resources. Even if you use the most powerful computer on the planet, you wouldn't be able to model 1 millimeter by 1 millimeter by 1 millimeter portion of this material. So we have to use assumptions. So we say these particles are inside a matrix. So these dots are our fillers. Of course, they are not smooth shapes, but then we say, okay, they are smooth shapes, and they are all similar in size. Now, I made two assumptions here. First, I assumed they are all same size, and then I assume, and they are smooth, and then I assume that they are smooth, which are not true. But without that, I cannot model. Then we say, so I have a matrix, I have a particle, because remember that this middle region represents this piece, but this piece, if you remember, it has many crystals in it. So each piece represents a crystal here, like a honeycomb. And then between the matrix and the particle, I have a region, let's call it a glue region, right? And the stiffness of that what we call interface is very strong for composite A, and then it will be very, very small for C. And then again, we make one more assumption to be able to model this in a finite element analysis and to be able to run it and to be able to analyze it. So we create an equivalent particle interface assemblage for the middle. So we say, okay, from this assumption, we go to this assumption where we have just matrix and the filler particle interface assemblage. We find their properties. Okay, Why are we doing these assumptions, these simplifications? So that I can put it in finite element analysis and solve it with 1 million elements. If I didn't do it, I will have 1,000 trillion elements. And there is no computer in the world that can solve 1,000 trillion elements. That is why. Now, the modeling procedure for the bulk modulus for composites studied heavily Hashin in 1962. He came up with the closed form solution. In 1974-75, Smith and then Christensen in 1979 derived the closed form solution for the shear modulus of two-phase composites. And then in 1967, Levin derived the closed form solution for coefficient of thermal expansion for two-phase composite. So we are still at the closed form solutions. We are trying to find the effective thermomechanical properties to be able to do our analysis. So finally, and then from here, we're using homogenization, right? Because in the element, in finite element mesh, I have an element. Inside the element, I can have only one elastic modulus, one coefficient of thermal expansion, one Poisson's ratio. This is my finite element, so I have to go from here to here. In 1994, Zhu and Chen, based on Eshelby's ensemble volume averaging, they derived the closed form solution to get the composite properties for this. Okay, so we are going to use these closed form solutions to go to micromechanics, because we are going from micromechanics to continuum mechanics. Now, and then I have to derive the thermodynamic fundamental equation of this composite material in order to account for the thermodynamics of the system, because everything they have done, like if you look at in the literature, Zhu, Chen's work, and everything is based on Newtonian mechanics. It means their equations are true for a brand new material on the first day. Second day, their equations are wrong. There is no entropy generation. To be able to introduce the entropy generation, I have to derive the thermodynamic fundamental equation of the material. So for a composite like this, the thermodynamic fundamental equation comes from the mechanical work, stress times strain. And if you divide that by temperature and rho, you get the specific entropy. Then you have some recovered elastic work, but this is not completely the elastic strain, but some part is recovered. Then you have thermal Joule entropy generation due to heat transfer. And then you have the heat generation in the system because of the internal friction. Now, however, for the stress here, when we calculate the stress at the finite element level, I still go back and calculate the stress in the matrix, filler, and the interface. So in the homogenization, I cannot just get rid of everything because they are not carrying the same level of, we assume that strain level is uniform, right? That is from basic mechanics, but the stress is not uniform. So that's why we modify the stress level that we use here. So as a result, the entropy generation that takes place in the matrix interface and polymer interface, I'm sorry, matrix interface and the filler are not the same. At each step, they are different. And I am not going to go into the how we put this into the formulation because we showed you, you just modify the universal laws of motion of Newton, and those are, that changes the differential equation of the, goes into the finite element. And then everything is implemented in abacus, right? Now, so if you compare with the experimental data, stress for strain, composite A, if you remember, composite A had adhesion promoting agent between the filler and the matrix. So the black is the experiment, I'm sorry, the green is the experimental, no, I'm sorry, black is the experimental data. And if you use a viscoplastic model based on like Zhu Chen's or a Shelby solution from the literature, this is what you get. But if you use the unified mechanics theory, you get exactly the experimental data. And then again, for composite A, at 75 degrees Celsius, of course, at 75 degrees Celsius, polymer has much smaller elastic modulus. Keep in mind that the glass transition temperature for this polymer is 90 degrees, and this polymer actually melts at 100 degrees Celsius. It is like a liquid at 100 degrees Celsius. So ultimate stress goes down significantly. But again, if you don't include the unified mechanics theory thermodynamics state index, you get this model, stress strain response. And then once you use the thermodynamic state index, unified mechanics theory formulation, you get the experimental data. Now, some of you might say, what the hell are you talking about? I have seen people predict composite material response using Newtonian mechanics. That is true. Shelby formulation, that is true. But what they do is, so they have this curve, okay? And they have this experimental data. Then they say, okay, our result differs this much. So they take a polynomial and then they do regression and they curve fit this difference as a function of strain, okay? And they call, that is their damage in the material, and they multiply their stress value with that polynomial, and they get exactly this experimental data. But I have bad news for you. The bad news is I don't call that science. That is not science. That is curve fitting. That is curve fitting. That is not science. They are cheating. Science is you derive the thermodynamic fundamental equation of the system from basic physics, and you don't use the test data to predict the test data. That is science. That is the difference between science and curve fitting. And then we looked at the system by changing the elastic modulus of the interface, because remember, our mission or task from the sponsor is to increase the lifetime of this product to 10 years. 10 years, one day is good enough. By playing with the elastic modulus or the stiffness of the interface, we can play with the fatigue life of this material. Okay, it is frozen again on me. Can you hear me?
Yes, we can, Professor.
You can hear me, but I don't know why my screen froze again. I think because of the snow, the computer froze. Let me try this again. Escape. No. Control Alt Delete. Okay. Let's see. Okay. This is working now. Control Alt Delete is my friend today. Again, so we also, if you change the thickness of the glue between the particle and the matrix, again, of course, you change the stiffness of that interface, and we try different thicknesses. And then we look at the damage in the system as a function of these parameters. And this here, the square, filled square is experimental measurement, and the solid line is the simulation from unified mechanics theory. And now we predict the simulations, again, using the unified mechanics theory for fatigue tests for different ABC, but keep in mind that in ABC, we are able to control the interface properties, and we are trying to change the fatigue life of this material. Okay. Okay. We look at the damage evolution of the composite at room temperature. Now, some of you might say, why don't you go point, we said the thermodynamic state index goes to 1, between 0 and 1. Why don't you go to 1, all the way that 1 in the experiments or in the simulations? Now, the customer doesn't wait until their countertop is falling into 2 pieces to show up at the store and ask for refund. If there is a small crack, okay, if there is a small, very small accumulation of damage that qualifies for warranty replacement, okay? So that is why we don't need to go all the way to 1, because we say, okay, 0.25 is good enough to compare with experimental measurement. Actually, most of the time, even less than these points is enough failure for the system, for the warranty to, the warranty is valid, according to the contract, warranty is valid even in the smallest hairline crack. So that's, therefore, the failure definition is not 1, it is 0.2, 0.3. I'm sorry, much below 0.3. So conclusions, what we discovered is the interfacial transition zone between the particle and matrix has great influence on the behavior of the composite. The acrylic particulate composite, this is called acrylic particulate composite, have very different mechanical properties between tension and compression. And we were able to successfully come up with a good model that improved their fatigue life for the warranty period they wanted. And the entropy does a very good job as a criteria for fatigue life prediction. So I'm gonna finish my presentation here. Stop sharing, and then I will take your questions.
Professor Jamal, there are a few questions in the chat box.
Oh, okay, let me go to the chat. First is, please register for the free webinar on metal fatigue to be held on 19/20. Yeah, those days, the Professor Rao's lecture is actually through the other Zoom website, so you will not be able to use this Zoom website to log in. So that's why you have to register.
Did we lose him?
I think we lost him.
That we can run
Mm.
for 3D is very, very small. So when we want to simulate an experiment, we have to run a 2D analysis. In 3D, we just use it to analyze it like a representative volume element.
Professor Jamal, we lost your connection. Can you just repeat the answer?
Oh, okay. Can you hear me now?
Yes.
Okay. So we run 2D analyses and 3D analyses. Now, if we want to simulate an experiment, we do only 2D analyses, because if we use a 3D analysis, it would take 2 years to run it. We don't have that kind of a computer in the United States. For 2D analyses, we can put a nice mesh and run it. So because of the for a representative volume element, you can run a 3D analysis. But for a test simulation, you have to run a 2D analysis because of the computational requirements.
Professor Jamal, I'm glad to hear this from you, because we did a similar work on concrete, to simulate concrete using something called as a unit cell. But of course, we used Newtonian mechanics and then did something there. And again, we matched the experimental work. So that was a few years ago. But we worked on concrete, and I also did, we did 2D analysis, and I'm glad that you also did 2D analysis, and that almost does the job.
Yeah, exactly. One day, hopefully, we will have strong computers, and then we can do 3D analysis, but right now we don't have them. Sir, how did you explain what is causing the early failure of zinc in layman terms to the sponsor? Okay, so their problem is they were using a adhesion promoting agent between the filler and the matrix, and the coefficient of thermal expansion is significantly different. Okay, so when somebody dumps boiling water, like in the US, they eat a lot of spaghetti, especially Italian Americans. They will dump the boiling water in the sink. Well, one has coefficient of expansion 88, one has 2. So as a result, immediately you are getting different stress levels in 2. So that was however, when you reduce the adhesion between the filler and the matrix, you reduce the transfer of the strain, and then you are able to reduce that problem. The kitchen sink might be subject to cycles of hot and cold water, and this could also cause cracking. Yes, they had that problem too. They had that problem too. Sir, can you please suggest how to extract a damage parameter interpretation from FEM simulation like Abacus? What do you mean extract? We don't extract damage parameter from Abacus. We derive our thermodynamic fundamental equation when we First of all, Abacus cannot do damage analysis because Abacus is based.
I'm sorry, I think we lost again.
But he doesn't know that we have lost him.
Yes, let him come back and
Sir, we cannot hear you. Can you?
Yeah, we lost him. Perhaps.
Can you hear me now?
Yeah,
No.
now you're better. Right.
Yeah, okay. Abacus cannot do damage. So if you want to do the models they have in Abacus are curve fitting models. That means you have to have the. Do you remember I was showing you the difference between the Newtonian stress strain diagram and the test data, and then you have to fit a polynomial in between. Abacus needs that polynomial to be able to give you the test data. For unified mechanics theory, you have to derive the thermodynamic fundamental equation, and then the laws of unified mechanics theory have the damage already in the differential equation. So when you put your UMAT, it is already in the differential equation. So your nodal information is not just displacement, but your nodal information or Gauss point information automatically is included in unified mechanics theory. Any other questions? Can you hear me?
yes, we can hear you.
Oh, good. Any other questions?
Hello, Professor. I am Arun Singh. Good morning. I have one query. Am I audible to you? Hello?
Yes, you're audible to us.
Yeah, thank you, sir. I have one query. When you are using this unified theory, this mechanics, how did you determine those parameters, those related constants?
I'm sorry, Dr. Singh, Professor Jamal will be online soon. He is losing connection a bit. Professor Jamal, can you hear us? Hello?
Can you hear me?
Yes, we can, sir.
Okay, good.
There was
Arun had a question.
from Dr. Singh.
Yeah, I have one query.
Yes, sir.
How did you determine the value of the parameters related with your model?
Like
That is
which
also a curve
parameter?
fitting. Yeah,
Which
that is also a
parameter?
type of curve fitting. How did you determine?
Which parameter? You mean elastic modulus?
No. In this unified mechanics theory, that
I don't have parameters.
there are some
in
equations.
unified mechanics. I don't
There are
have
some
parameters.
constants. There are some constants
Yeah.
that
Okay.
that will depend on the what type of phenomena you are studying. For example, I saw that EMS there was one constant molar mass. So how that value is determined? Am I audible here? I think again.
You are audible, sir. And in between, we are losing the connection.
I think their snowfall is very
Yeah.
outside.
Yeah, it's
It's visible from windows.
right.
Again, no, anyway, I can also send the message to him. So
Yeah, I can answer to that question. if
Yeah.
you want. Yeah.
In fact, I wanted to ask that question.
Yeah,
You
the material parameters are material parameters only. They are very well known. For example, molar mass is constant for a given material. And I'm not sure about other parameters which are used in his model.
Because suppose even we are using some models derived from physics, then there are some parameters. Then obviously we have
Can
to
you
fit the
hear me now?
experimental. Yeah.
Can you hear me now?
Yes, sir, we can hear you.
Okay, sir. In unified mechanics theory, all the parameters we need are from the periodic table.
Okay. Right.
So molar mass, gas constant, Avogadro's constant, that is all I need.
Correct. Thank you.
You're welcome, sir. Yeah, the weather here is really bad. That is why our internet connection is very bad. Many towers are, I think, collapsing. Any other questions?
So
Any other questions, participants?
How about Ramesh Kumar? Are you here? You see, Ramesh is not even here. How about Brahma Datan, VB?
he's there.
Okay, Brahma Datan, do you have any question? Sir,
Hello.
do you have any question?
Hello, sir. Hello. Can you hear me?
Yes,
Sir?
yes. Do you have any question?
Yes, sir. That how the micromechanical based concept is converted to that continuum based modeling, sir.
Yeah, that is a lot of mathematics. I'll be glad to share the papers with you. I'll be glad to share the papers with you, but that mathematics would not fit into just 40-minute lecture. But I'll be glad to share the papers with you. If you send me an email, I will send you the papers.
Sir, one more thing, sir.
Yes.
If we consider ceramic material consists of several micro crack, how we can approach that type of problem, sir?
I'm sorry, I couldn't follow you. What do you mean cracks?
Yes, sir. Ceramic may have several micro crack when we manufacture those type of material. So when we want to do the model this such type of material, how we can approach?
Yeah, so you have a good point. What if we have a crack inside the particle itself from manufacturing? Right?
Yes, sir. Yes, sir.
Yeah, so that would be easy to model from our perspective. But however, we didn't have the facilities to be able to do testing inside the particle, the filler particle itself, the ATH, the ceramic. But you can include that as, because thermodynamic state index doesn't have to start from 0. It can start from, let's say 0.1, 0.2, because you already have a crack. But you have to measure that. You have to know that there is such a crack. Of course, if you just ask the vendor, the company that sells it, they say, no, they don't have any crack. It is perfect. So it has to be investigated.
Okay, thank you, sir.
You're welcome. How about Tiru Sentil Adhiban? Are you here? Tiru Sentil Adhiban. N. Not here. How about Mr. Mangal?
No doubt as such, sir. Thank
Okay, I couldn't hear you. What did you say, Mr. Mangal?
Sir, no doubt as such. Thank you, sir.
Oh, okay. You have no doubt. Okay, okay. That's fine. Okay, my time is up for today, so I don't want to take up your too much time. I don't want to pass my time limit. So we guys talk to you tomorrow. Have a good evening.
Thank you. Thank you, sir.
Thank you. Bye-bye now.
Thank you, sir.
Thank you all. I'll hand over the session to.
I think Ashish has some announcements regarding our schedule on Wednesday.
Yes, sir. Audible, sir? Hello.
Ashish, you're not audible.
Am I audible now, sir?
Yeah, slightly better. Yes.
Okay. So thank you, Professor Basran, and thank you, Naushad, for the session. Thank you all for attending. And now I have a small information to pass. That on 19th, we have actually 4 sessions. The sessions will start from 2:30 p.m. in the afternoon.
3:30.
3:30, sir.
3:30.
3:30 in the afternoon, and then we have a 1.5 hours of webinar on metal fatigue, which is organized by Professor Basran. So for that, it's a free webinar. I have given the link in the comments in the chat box, and I will send you a personal mail also. And so please register through that. So the Zoom link will be different from this Zoom link for that particular event. And then we will have a regular session from 5 o'clock to 8 o'clock on 19th. So you can click on that link provided in the chat box, and after this session, I'll also send all of you same email. Also, you can check there also. If many of people are not present today, maybe they want to join that time. And tomorrow we will be circulating a similar form for certificates by getting the guidelines from our CC, what are the information they are requiring. And most of the time the certificates will be sent online only. So if they want to send by post, another method is there. I have to inquire about that also. But generally they are doing it online only. Sir, for now, that is
tomorrow the first session will be a special session. The head of our teaching learning center will share some perspectives about online teaching. So many of us teachers may have a lot of things to learn from that. It's a new experiment that all of us are going through during Corona times of online teaching. How effective they are, how effective they are not, and how to improve them, etc. There's a lot of experience that he has gained by talking to a lot of teachers and all that he will share with us. So please don't miss that at 5 o'clock. And of course, 6:30 you have Professor Shivkumar talking of shape memory alloys. So there are a lot of interesting things tomorrow.
Shall we wrap up, sir? Then I think this was the information we have to convey.
Thank you.
Okay. Thank you all.